Hello everyone, I'm Xizhe, a postgraduate student in the Internal Combustion Engine Research Institute of Tianjin University. Today's topic of my presentation is research on collaborative control strategy of hybrid models based on economic and emission. Well, my presentation is divided into 5 parts. The first part is the research background. Nowadays, all walks of life are facing industrial transformation and upgrading, and the automotive industry is no exception. In recent years, the state has issued a number of policies to promote the development of new energy vehicles, including plug-in hybrid vehicles, pure electric vehicles, and fuel cell vehicles are still limited by technology or infrastructure, while plug-in hybrid vehicles have the advantages of high efficiency and energy saving of pure electric vehicles and long endurance and strong horsepower of traditional vehicles. And in view of the above problems, there is little research on the above specific problems at home and abroad. And most of them take P2 and PS vehicles as the research objectives. Most of them only optimize the economy and rarely consider the emission problem from the perspective of vehicle control strategy. Most of them only consider single objective optimization methods, and there are few multi-stage and multi-objective optimization methods for emission and economy. Therefore, in view of lack of research on P13 hybrid electric vehicle and lack of research considering emissions and economy at the same time, taking plug-in P13 HEV as the research object based on CDCS energy management strategy and taking the cooperative control of economy and emissions as the research goal. A single panel for the control strategy is designed to improve economy and reduce emissions at the same time. And multi-objective optimization control strategy to jointly control emission and fuel consumption. And the second part is the vehicle model. As you look, the power system framework of plug-in P13 HEV is shown in this figure. It is composed of one engine, two motors, P1 and P3. A battery, this is a battery, and a special gearbox. Through the opening and closing of the clutch, and the start and stop of the engine, the conversion of pure electric series and parallel models can be completed. Some parameters of the power system are shown in this table. On this basis, the vehicle longitudinal dynamics model and the engine model based on map are established. This is the map. Model a motor model, battery model, and a drive model based on PI, closed loop control. Okay. Based on this and the basic energy management strategy based on CDCS, the third part designs a single panel control strategy based on fuzzy logic. Firstly, the basic braking recovery circle map based on the accelerate panel is formulated. The basic negative circle is related to the accelerate panel opening and the vehicle speed. The overall design concept is that the braking recovery circle decreases with the increase of the pedal opening, and the braking recovery circle decreases with the increase of the vehicle speed, so as to maintain the driver's normal driving habits as much as possible. On this basis, the map is reasonably correct according to the change rate of accelerate pedal. In order to effectively avoid frequent positive and negative circle switching due to drive misoperation. When the change rate of accelerate pedal opening is less than -5% and the vehicle speed drops for 0.5 minutes, it will select braking recovery circle map for accelerate panel output circle. Otherwise, select driving circle map. Among them, the 0.5 minutes is the calibration value. The greater it is, the greater the safety margin is. But the sensitivity is reduced. It can be used as a manually adjustable value for the drive in the actual vehicle. As shown in this figure, we used the fuzzy logic controller to correct the braking map, takes the accelerate pedal opening and the change rate of accelerate pedal opening as the input of the fuzzy controller, and takes correction coefficient as the output of the fuzzy controller. Finally, multiply the correction coefficient Kf with the basic braking circle to obtain the final braking circle. The first is the formulation of the membership function. There can be no empty set in this membership function. The greater the slope of the membership function, the higher the sensitivity, and the smaller the slope, the higher the stability. The second is the formulation of fuzzy rules, which represents the driving attention. In short, the accelerate pedal opening and the change rate of accelerate pedal opening are forced into the membership of different language variables. The membership of the reasoning results is obtained through the reasoning rules of the language variables. The faulty reasoning results are falsified by the center of gravity method. And finally, regenerative braking recovery coefficient between 0.8 and 1.4 is obtained. The fourth part is a multi-objective optimization algorithm based on neural network genetic algorithm. Okay. The framework of the whole algorithm is shown in the figure. That is, establishing the optimization objective and dataset, neural network fitting, genetic algorithm optimization to obtain the engine operation curve under the engine series working condition. Okay, first, the optimization objective is established through preliminary simulation analysis. It is found that there is a negative correlation between NOx emission and fuel consumption. Therefore, establish nitrogen oxide and fuel consumption as multi-objective optimization object. And the commonly used multi-objective optimization methods that is, the multi-objective optimization method based on weight can be expressed by this formula, where Fx is the universal characteristic curve of NOx and fuel consumption, and x is the vector. In this, the speed and power are expressed, and the omega is the weight coefficient, which is also the parameter we need to optimize next. Before that, the data shall be normalized, and the 200 group of simulation data shall be obtained through 4 cyclic acquisition and data sorting. The concept of comprehensive index is proposed, and the formula is finally obtained. Okay, so about 200 groups of data are shown in this figure. That is, as the input samples of neural network fitting drops the feedforward neural network model. The hidden layer is 1 layer. The number of neurons is 20. The hyperbolic tangent function is selected as the transfer function. of the hidden layer, and the line function is selected as the transfer function of the outer layer. Through the above boundary conditions, the neural network is trained to achieve the target mean square difference and complete the curve fitting in the 22 generation. Then the parameters of fitting function expression are extracted. The weight coefficients and the threshold coefficient between various levels are extracted through statements, and then the expression is extracted through inverse normalization. Okay. Next, the boundary condition of genetic algorithm are shown in the table. After 148 iterations, the function tolerance value is finally reached, and the calculation is stopped. The variable value corresponding to the best fitness is omega 1 and omega 2. Therefore, the multi-objective optimization with coefficients optimized by neural network genetic algorithm are omega 1 and omega 2. The corresponding relationship between series power and engine speed and torque can be obtained through multi-objective optimization calculation. Finally, the fifth part is simulation analysis. Okay, firstly, the effectiveness of the single panel control is proved. As can be seen from the figure on the right, under the WLTC cycle condition, the fuzzy single panel control significantly reduced the frequent slight braking of the brake pedal. That is, the vehicle can reach the desired running state without changing the driver's driving habits. In the steady state, the single panel control can effectively improve the energy utilization, improve the economic performance of the vehicle, and reduce emission. Compared with the fuzzy single panel control, the SOC is increased by 1.63%, and the energy is increased by 4.7%. In order to continue to verify the effectiveness of the algorithm, a more intense drive pedal model is established, and the driving milligo of 1,500 meters is selected as the characteristic point. As we can see, in single panel control, SOC is saved by 3.5%, and the energy saving rate is as high as 43%. The right is CS state. After using single panel control, the fuel saving rate is 0.87% on the basis of SOC consumption decreasing by 0.02%. In order to continue to verify the effectiveness of the algorithm, continue to use driver panel model established in the city stage, and selected the driving legal of 2000 meters as a characteristic point. During single panel control, SOC is saved by 1.03%, and the energy saving rate of electricity and fuel is 43%. That is, the comprehensive energy saving rate is 43%. Including in the simulation environment, for the single panel control strategy in CS stage is consistent with that in CD stage, which can effectively improve energy utilization. Okay, next is the simulation of multi-objective optimal control. On the left are the simulation results based on economic optimal control strategy and emission optimal control strategy. The first finger on the right shows the multi-objective optimization simulation results based on simple weight distribution. Compare with the simple weight distribution control strategy. The fuel economy performance improved by 0.04%. The emission performance is improved by 1.26%, and the comprehensive index IC is improved by 67.98%. Compared with the benchmark strategy, the fuel economy performance is reduced by 0.37%. The emission performance is improved by 3.37%. The comprehensive index IC is increased by 8.18%, and the comprehensive performance of the whole vehicle is improved. This is the end of my presentation. Please criticize and correct me. Thank you.